Correct? Okay, it's good to know. So wherever you are, good evening, good afternoon for us here, and good morning in other parts of the world. I'm pleased to welcome you to this side event on nanomaterials and nanometals and used batteries, which has been organized by the Government of Uruguay, a co-lead country for the development of the Basel Convention technical guidelines on waste batteries and the Global Alliance for Health and Pollution. So unfortunately, Rolf Payet was not able to make it this evening, but I'm very happy to stand in for him and provide this statement on his behalf. The use of nanomaterials and nanometals in batteries is reported to be employed to improve the efficiency of both lead-acid batteries and other batteries, for example, lithium-ion batteries. But what happens to nanomaterials when the batteries are dismantled, crushed, and recycled? And what happens to the nanocomponents with the batteries that are disposed of in a landfill or stored for many years? What we do know is that despite being often composed of known chemicals, metals, metal oxides, carbon structures, the small size of the manufactured nanomaterials and nanoparticles can lead to different behavior from the bulk phase. This is most related to nanomaterials and their very high surface to volume ratios, quantum effects, and potential to cross biological borders due to their small size. We do not know a lot about the behavior of nanomaterials in waste and in waste batteries. For this reason, the parties to the Basel Convention decided to keep under review the issue of waste containing nanomaterials, requesting information on risk posed by waste containing nanomaterials to be shared. The issue is of particular relevance because of the precautionary approach to the exposure to nanomaterials in waste batteries during recycling and final disposal. And this is currently being debated among experts involved in updating and development of technical guidelines on the environmentally sound management of waste lead-acid batteries and other batteries, including lithium-ion batteries. These technical guidelines play an important role in complementing the engagement of the Basel Convention in addressing e-waste pollution, which was initiated more than 20 years ago with the adoption of the first version of the technical guidelines on the ESM of waste lead-acid batteries, and that was in 2003. The debate on nanomaterials in waste batteries is of great relevance, considering the massive generation of waste batteries foreseen in the next decades and their potential environmental and health impacts. The recycling of waste batteries is crucial to address other global environmental and health challenges, such as climate change, environmental impacts of primary mining, and lead pollution. As you know, batteries are key components of digital and renewable energy technologies. Their environmentally sound management contributes to reducing greenhouse gas emissions and mitigating climate change. Primary metals and minerals can cause erosion. The mining of minerals and metals can cause erosion, loss of biodiversity, or the contamination of soil, groundwater, and surface water by chemicals emitted from the mining process. Waste batteries recycling can reduce the reliance on primary mining of minerals and metals when countries are increasingly concerned about the scarcity of metals and rare substances included in the batteries. Finally, workers, informal recyclers, and vulnerable populations are around hotspots where lead-acid batteries are recycled. Risk exposure to lead also, when present in a nanomaterial, can lead to significant public health problems, particularly in young children and pregnant women. In this scenario, exposure to nanomaterials in waste batteries can represent a significant co-risk factor where also other sources of nanomaterials enhance the magnitude of exposure of human populations and the environment to adverse effects that are still being discovered and identified. This is why today's side event is very important, not only to support the development and updating of the technical guidelines, environmentally sound guidelines on environmentally sound management of waste batteries, but also to raise awareness of waste containing nanomaterials among the participants. As I round up my remarks, I would like to thank the organizers of the side event for the opportunity they've created to discuss and share experience on nanomaterials in waste batteries so that the technical guidelines on ESM of lead-acid batteries and other batteries can reflect the best knowledge available on how to protect human health and the environment from the adverse effects of nanomaterials in waste batteries. With these few words, I'd like to express my sincere appreciation to all for your participation. Thank you.
Thank you very much for these wonderful opening remarks that are a very good starting for the dialogue of this afternoon. This side event has been organized by the Global Alliance, co-organized by the Global Alliance on Health and Pollution and the Government of Uruguay. So the Government of Uruguay will help with the questions and answers and the closing remarks. Here, Judith Torres to my left, and Maria Paola Lia, the Executive Director of the Global Alliance on Health and Pollution, will give the welcome words to everybody. Thank you, Maria Paola.
Thank you, Lilian. Welcome, everybody. Welcome to the people in this room, to the co-organizer and our partner, the Minister of Environment of Uruguay, that we're very lucky to work with, and all the panelists and speakers, and all of you. My name is Maria Paola Lia. I'm the Executive Director of the Global Alliance on Health and Pollution. We are a Swiss foundation based here in Geneva, and we collaborate with a number of low and middle-income countries and globally, addressing pollution issues which have an impact on health outcomes. And one of the regions where we work, and we have been very lucky to establish very strong collaboration, is the region of Mercosur. And Uruguay is one of the countries where we can share our experience and bring what we learned in other parts of the world, and at the same time learn from the leadership of this country in the region and see what we can bring outside. This evening, the event is on nanomaterials because we thought it would be relevant to share with you what the speakers will illustrate us. But of course, our work goes beyond this. In the region of Mercosur, we work on used lead-acid batteries. In other parts of the world, we address other chemicals, air pollution, so a number of issues depending on the country's priorities. But I think today we want to listen to our speakers. I just wanted to welcome you all and introduce me, and also share that we are a collaborative alliance of more than 70 members and observers, and we are open for new members to join the alliance. So I wanted to share with you this invitation to visit our website, contact us afterwards if you have questions, and also ask me how you can join to be part of our alliance. Thanks.
Thank you very much, Maria Paola. And now I'm proud to say that we have very high scientific and technical experts today, 2 online and 2 here with us. And the first one that will break the ice is Claude Chanson from Recharge. He's the General Manager of Recharge, who covers Europe's most relevant battery manufacturers at all aspects of the battery industry. He's an expert for partner for all technical and legislative topics, as well as with related laboratories and institutes in Europe and at the international level. So thank you for being with us.
Thank you for the kind invitation, and happy to contribute to this panel. In a few words, Recharge is an industry association. We represent the value chain of the complete manufacturing until recycling of batteries in Europe. And I would be happy to share some information with you about the usage of nanomaterials in batteries, why we are using, and how we are dealing with it. Next slide, please. Yes, so that's just a title. You have just a quick overlook of our membership, and you can see here, of course, that let's say big names of the worldwide industry is now involved with the battery industry, because you can find batteries everywhere, from automotive to laptops, cell phones, and power tools, big machines, everywhere. So that's our membership. Next slide, please. So I have just wanted to present you a little bit of what batteries are and the chemical composition of batteries and why we are using the nanomaterials. And I will certainly leave the end-of-life discussion to other speakers. Next slide, please. So that's the batteries. As I said, they are now everywhere, and from laptop to mobile phone to space. So you have probably 1 or 2 or 3 or 4 batteries on yourself right now. Next slide, please. So the general principle of how batteries manufacture, it's in principle rather simple. You have what is called an anode, then a separator, and then a cathode. And then you put, you make a coil or a flat format with that, and you put it in a metal casing. So that's the general principle. Next slide, please. And there are typical 3 formats, which are round cells, a metal case, and now a lot of are called polymer batteries or flat or soft casing. And a lot of new products, very flat, contain the one you can see on the right side, the soft casing, because they have less weight and more energy in the single format. Next slide, please. And then with these cells, you do a lot of things, from small batteries to very large batteries. And you can here some examples of a famous battery manufacturer for electric vehicles, which is using thousands of cells in a big battery. But you also have sometimes examples where you have large batteries inside large systems. Next slide, please. So let's talk about chemistry now, because that's really the part which is of interest for us. And here you have a picture showing 2 major types of batteries. And this is about the example of lithium batteries, but also applicable to other chemistries for batteries. One is called, and it's classified under the UN number 3480. It's a lithium-ion battery. And it's, in fact, made with a graphite anode on the left side and a cathode, which is made of powder of metallic oxide, generally. And in between them, you have the electrolyte and the separator. And on the right side, you have the same systems, but the anode is made of metallic lithium in this case. So a number of batteries, lead-acid batteries, are also using metallic lead as an anode. So that's the typical configuration you can find for lithium batteries and others. Next slide, please. So now we come to the functioning of the battery. So this diagram is showing, for the example of lithium batteries again, how a battery is functioning. Everybody knows that outside of the battery, of course, you need to connect an electric circuit. That's what it's made for. So you have electrons going around, but inside what is moving, it's ions. So in this case, it's lithium ion. But in all batteries, you have one type or another of an ion which is moving. In lead batteries, you have a lead moving in the electrolyte. And then you have ions which can be alkaline or acid ions, like water-based. So here, the lithium ion is moving from one side to the other during charge and discharge, and is intercalating in the electrodes. And looking at this, you already understand why are nanomaterials interesting, because the reaction is at the atomic level. What are moving is atoms, ions. And if you want to keep the maximum space for these atoms, you see here these kind of layers, which have been schematized here. The ideal layer is one layer for intercalation, one layer for an atom, another layer for intercalation, and so on. And then you directly understand that this is driving the interest of electrochemistry to nanomaterials, because they can interact with, as was mentioned in the introduction, with very high surface and very limited quantity of material. That's the optimum. Next slide, please. So maximizing this electrochemical interface is true for everywhere. And there are 2 ways, in fact, to achieve high interfaces. Either you start from powders, and then you understand that the smaller the powder, the higher the interface. Or you start from massive material, and when it's a case, for example, as you have seen for the metallic anodes, and like the lead or the lithium metal anodes, and in this case, this kind of redox systems, in general, they are not really considered as nanoparticles. Of course, the metallic is massive, and then it is dissolved during the redox oxidation, and then precipitated again on the metallic phase. So it's kind of fine shapes, but it's based on the massive material. It is, of course, different when you start, like for example, lithium ion, with nanoparticles or very small particles. So next slide, please. Practical example of the chemistry we are using, and that's where things become complicated. Until now, it was high-level principle, but of course, reality is always much more complicated, and that's where you need specialists. You have this drawing here showing you, among years, all these colors represent a different lithium oxide technology. And you see that is corresponding to what is placed on the market from 2022 and anticipated to 2030. And you see things are changing permanently. Permanently, new design, new chemical composition of these cathode materials are discussed. So this is due to permanent technical progress, and therefore it is very difficult to really discuss about the nature and the composition of this material. So you know that in this oxide, you have nickel, you have cobalt, you have manganese. That's what means this NMC initial you can see here. It's about nickel and manganese and cobalt. But the composition is completely changing over years. And also what is changing is the size of the particles which are used. Next slide, please. So I did here copy some title of some general papers which are discussed at the moment. You have some articles published in 22, you know, very recently, or 23, and it talks about lithium iron phosphate in this case, which is clearly identifying that the best optimum they are promoting is to go to smaller particles, and that's what I was saying. As you can see on the picture here, you can see picture A is some kind of ball. This is not nano size, so it's not 10⁻⁹ to the meter, it's micro size, it's 10⁻⁶. And then you see that, of course, when you look until from A to B to C and D, then D is indeed the nanoparticles, which are typically on the size of 100 nanometers in dimensions. And they are aggregated in these spheres of about some micrometers. So that's typically the materials we are discussing when we discuss about nanomaterials in lithium batteries. Next slide, please. So, as I said, where are they used? Well, for lithium batteries, almost everywhere, until now, because that's the best way to proceed, to have these ions moving everywhere and having very good access to the material. And you can see here from the bottom to the top, what is currently the level of generation of product. So the basic line, which are called LFP, NCA at the bottom, they have a carbon anode, and carbon also can have some nano aspects, despite the particles also are more micro than nano. And then you have all of this new generation coming up, and in principle, all of these will continue using nanomaterials. Well, I have a question mark on the top. You see generation 4B, it's talk about something you may have heard about. Solid state batteries, that's the next generation batteries. Solid state, which is not using anymore liquid ions moving like it was showing in my diagram, but ions moving in solid state. And that's really a different game. And here we are not so sure how it will be manufactured and whether we will go through these nanoparticles or not, because that's still under development. So I still have a question mark, but this is for the future generations. Next slide, please. So that's, in a very short, my introduction on why and where are the nanoparticles used in the batteries. So clearly, battery contain nanomaterials intended by design, because that's a more efficient design to optimize the electrochemical reactions. And based on the permanent technical progress, we cannot really say, oh, that's exactly this composition or that one, because you have multiple generation of product, we can be more generic that these, or for lithium batteries, all of these materials contain metal oxide, because these particles are made of metal oxides, and they stay until the end of life. When it's come to metallic, it's a bit different. And so I put the lead acid batteries, because you mentioned several times lead. I'm not so well aware about really massive usage of nanoparticles in lead acid. The interface may be nano, because the interface needs to have a strong structure to react, but it's based on the massive material. And these reactions that are transforming the lead during each charge and discharge are also contributing to kind of massification of the material. So in general, at end of life, you certainly can expect to have nanomaterials in lithium batteries, much less of that in lead acid. Of course, lead is still lead, and you have all the reaction of lead, but the nano effect on lead, I am doubtful this make any significant change to the lead battery hazards. Then the battery industry, of course, is dealing with this issue and questioning, of course, this safety of usage of these nanomaterials. We are working openly and happy to contribute with potential help here, understanding the work of this group on understanding the battery end-of-life hazards by indeed providing our expertise and knowledge about how to protect, first of all, the industry, so the manufacturing industry, but also the recycling industry, by all of these, particularly in Europe, these health and safety requirements that are applicable to batteries. You may know that batteries in Europe are heavily regulated already. I was thinking about your proposal of mentioning batteries being, sent to landfill, which is impossible, completely forbidden in Europe, but unfortunately not all over the world. That's a big difference. But we're happy to contribute with our knowledge and expertise in Europe to support this group. Thank you for your attention.
Thank you very much. Really, thank you very much. It was a very interesting presentation. I'm so sorry it was so short. I'm sure there will be many questions at the end. So now we have the next presentation is threats and benefits posed by nanotechnology. And we have Vivian Howard, Dr. Vivian Howard, from the Biomedical Science Institute of the University of Ulster, fellow of the Royal College of Pathologists, past president of the Royal Microscopical Society, and member of the International Society of Doctors for the Environment. He is online, so Dr. Howard.
Yes, can you hear me?
Yes, thank you for being here.
That's okay. And I can't use the camera apparently, so right. I'm a pathologist and toxicologist. I spent the last 15 years of my research life before I retired looking into the toxicology of nanoparticles. And so the benefits have been spoken about in the previous talk. You clearly get increased functionality by going for smaller particle size. So my intention is to tell you what I know about the possible threats of exposure to nanoparticles. And I want to do this looking at the evolution of the human and other biota on the planet. Can I have the next slide, please? Right. So mankind and other animals have been exposed to nanoparticles throughout evolution. They're mainly soluble crystals, typically from the resuspension of salt from the sea, the action of the waves, but also biological nanoparticles such as viruses. So the thing that's changed is that nanoparticles are being engineered now, and they're pretty insoluble, most of them, and that is brand new. But many of the transport mechanisms that have been there since forever can carry them around. So I first got interested in this when I listened to a lecture by David Jefferson. He's a crystallographer. When you take something like gold or platinum, which is completely inert in the lump, in a large lump, when you make it into crystals, little nanocrystals, there become disparities between the number of nuclei and the number of electrons, and they become electrically charged, and then they become chemically reactive, and that is indeed how we make heterogeneous catalysts. So the basic question we have to look at is what is the interaction between this surface chemistry? It's called Fenton chemistry, and wet biochemistry, which is us. So that's what we're going to talk about. Next slide, please. Okay, so the first thing to understand is that cells have nanoappetites. On the right is a scanning electron micrograph of a macrophage trying to take in some asbestos fibers, and you can see that they're too big to do that. But there are two basic mechanisms by which particles can be taken inside cells. One is called phagocytosis, which is shown there on the left. This is for larger particles between 1 and 2 microns, that's 1,000 to 2,000 nanometers, and it's an engulfing mechanism. But there's another one called endocytosis. The predominant one is pinocytosis, which is the Greek for cell drinking. And these are little invaginations of the cell membranes, and it's a continuous process, and it takes in things about the size of nanoparticles. And indeed, this is the way that viruses get around the body. So nanoparticles can hijack the same system that viruses use. And you can see some references there at the bottom. These are papers which show how they've been detected, engineered nanoparticles have been detected in liver, spleen, heart, and brain. So they get everywhere, basically, in relatively low doses. Next slide, please. So what early research into this is the work of Ken Donaldson, is that it doesn't really seem to matter too much what things are made of. They have a common property. So here you have on the left, you can see is the amount of inflammation that is induced in the lung by particles of different size. And it's looking at titanium dioxide or latex or carbon black. Those are the three things that looked at. And if you can compare the fine particles, that's PM 2.5, with ultrafine particles, which are nanoparticles, you can see that the amount of inflammation that's induced, that's the white columns, is much higher than for the larger particles. And this is to do with this surface chemistry. They can induce reactive oxygen species, and they seem to have a common ability to induce inflammation in the body. Next slide, please. So you have to think about the pathways, portals of entry, and those are the usual things that we think about in toxicology. So you can breathe them in, and they can get across the air-blood barrier, which is only about 150 nanometers thick. They do that by pinocytosis. They can get in through ingestion, and there's debate about whether they can get across the skin. And then you have to think about where they get to. I've just mentioned some of that. And can they be excreted? Well, yes, they can. And what interactions do they have in the body, and can that lead to toxic effects? So let's have a look at that. Next slide. So these are the basic questions. One, how many particles get to a particular target? And two is, does it matter if they do? Are there any effects? Are there negative side effects? And this is what, as I say, I spent 15 years of my research life doing. And the answer to question one, where do they get, is rather more straightforward than the answer to question two, which people are still looking very much into. Next slide. So the cellular vulnerabilities are interactions with macromolecules, so proteins, DNA, RNA, phospholipids, which are what form cell membranes. And the toxic effects of such interactions can be genetic or cancer-causing or immunologically toxic or reprotoxic. Next slide. So there are various sites of a special cellular vulnerability. So one is the maintenance of integrity of cellular membranes. The second thing is all cells need to burn sugar and have aerobic respiration. And this takes place in the mitochondria, which is where you get ATP production. And then another one is protein synthesis. We need proteins to run our bodies. And this is a complex folding process to get a functioning protein, and that can be perturbed. And then lastly, the preservation of the genetic apparatus in the cell and the repair of damage to DNA. Next slide, please. So the mechanisms that have been considered for nanoparticle toxicity are catalysis. So we've already talked about that. The next one is membrane perturbation, and that's by two methods. One is by lipid peroxidation, and the other one is by surfactant effect. So some of these proteins that can be formed are surfactants. They're a bit like detergents. Then there's chaperone effects on proteins, which means that there can be misfolding of proteins, and this is quite a considerable worry in the long term. And then there's direct physical damage, and you could see from that asbestos image at the beginning how that could cause physical damage to a cell. Okay, so just to finish off, a few papers each of which demonstrates one of these. I think there's a lot more in the literature now since I retired about 10 years ago. And there is a review paper by Elsasser and Howard in which Lillian has a copy of, and I'm sure she can let people have it. It's called The Toxicology of Nanoparticles, so it goes over much of this. Next slide. Okay, so this was fullerenes. These buckyballs, as they're called, and they can get they're quite small, and they can get around by pinocytosis, and you can see them here collecting in mitochondria inside a cell, and their effect would be catalytic. So they have the ability to generate reactive oxygen species, and that was in a paper by Foley. Okay, next slide. So membrane perturbation, we need membranes to be able to, our cells need membranes to be able to function properly and partition cells into different places. And so lipid peroxidation is one method of damaging these phospholipid bilayers, which are what cell membranes are made from. And it eventually leads to cell death if it's severe enough. So this was a paper here by Kamat et al., which goes into some nanoparticle interactions leading to lipid peroxidation. Next slide. Okay, then there are surfactant effects. Some nanoparticles are made by the body when proteins misfold, and these are called oligomers and amyloid forming peptides. And these are strongly surface active. And I'm just coming on to the fact that protein misfolding might be associated with exposure to insoluble nanoparticles. Next slide. So these are diesel particles on the left. They're quite small. And the same scale on the right is the centriole, shown by electron microscopy in a cell, and you can see it's about 100 nanometers across. So some of these nanoparticles are small enough to be able to get inside processes. So these centrioles are where some proteins are manufactured. Next slide. This is almost the last one. So this paper by Bilston showed that silicon nanoparticles, about 9 nanometers in diameter, when stabilized with a protein, in this case the protein was carbonic anhydrase, you get a change in the circular dichroism spectrum, which basically means that they've ended up with the wrong shape. Now, once you get the wrong shape, so they're tapped out as a string as a polypeptide, and then they have to fold in certain ways to secondary, tertiary, and quaternary structure to be fully functional. So here's a direct example of a nanoparticle interfering with that process. Next slide. There are 42 known protein misfolding diseases in humans. They're mostly in the central nervous system because that's the organ which can't repair itself by making new cells. The neurons that you have around birth and just after birth are the ones that have to last your lifetime. And there are mechanisms for collecting misfolded portions of proteins. There are sort of graveyards within these cells. But if you jack up the rate at which misfolding occurs over a lifetime, then you're likely to see some negative effects or the earlier onset of certain diseases. So Alzheimer's disease would be one possibility, or Parkinson's. So that's a real worry, is that in the long term, exposure to insoluble nanoparticles, which you know can get to the brain, might interfere with and lead to degenerative disease via this process of protein misfolding. Okay, next slide, I think, is conclusions. Yeah. So there are clearly commercial benefits for using nanomaterials, and this is down to increased surface to volume ratio, which has already been discussed. So I think that while nanomaterials are fully contained in batteries, they don't pose an immediate threat to users, that's clear. However, I think we have to be very careful about disposal. And if they're released into the environment, or maybe pose health threat to workers. And it will be critically important to assure that they're disposed of safely, particularly avoiding inhalational hazards. That's, I guess, what I had to say, Lillian. Thank you very much for your attention.
Thank you very much, Dr. Howard. Please stay for questions and answers, and thank you for helping us to understand how the burden of disease of nanoparticles and nanometals can influence our burden of disease. The next speaker is also online, Lorraine Joshua. She will present nanomaterials in European chemicals legislation, current status. Lorraine is a regulatory engineer of the environmental policies team with experience in regulatory support services in the field of the European chemical regulation, like REACH and CLP, of the Research and Innovation Department of Luxembourg Institute of Science and Technology, LIST. Lorraine, welcome. The floor is yours.
Thank you very much, and thank you for the invitation to do this presentation today. So as you mentioned, I will present the current status of nanomaterial in European chemical legislation with a focus on REACH, CLP, and also the battery regulation. So maybe we can go quick on the first slide, because it's presentation you already done, which is about the list and the environmental policies. So the next one also you can pass the slide, and the next one will be what I will present today. So for the next slide, please. So as mentioned today, so I will talk more about European chemical legislation and nanomaterials. And first of all, I wanted to give you a generic overview about chemical in EU legislation. And you can see on this slide, we can see we have 3 types of legislation in Europe. The horizontal legislation, which addresses really broad aspect of all chemicals. So we have, of course, REACH and CLP, which addresses safety in a really broad aspect around chemical. But we can have also Seveso concerning all manufacturing plants, the worker protection legislation, and also several environmental legislation like Waste Framework Directive, the Water Framework Directive, or legislation around pollution control, which are regulation that ensure we have not harmful chemical in the environment, and that we have some monitoring to be sure that there is no problem with these chemicals. But we have also some sector-specific legislation. So in that case, it's chemical legislation that have specific scheme of approval about certain use of chemicals. So you need usually an authorization to place on the market this product. So we have cosmetics, pesticide, biocides, medical devices, for example. And we have also legislation that really address specific properties of chemical. So we have the POP regulations, so the persistent organic pollutants, which implements the Stockholm Convention and Aarhus Protocol. I can also mention PIC, so prior informed consent regulation, which implements the Rotterdam Convention. Next, please. Also, before going more into details of REACH, CLP, I wanted to come back of the evolution of different actions that introduce nanomaterial in EU legislation. So we can see we start to have some work 20 years ago with the European strategy for nanotechnology. And we have several actions about the Commission. So in the gray boxes, it's mainly EU publications. So we have preparatory planning documents. We have also some staff working documents that usually analyze the current status of legislation in Europe that address nanomaterials. And you have also the recommendation concerning the definition of nanomaterials. The green box is related to the European Parliament action concerning nanomaterial in legislation. And in the blue box, it represents some research projects undertaken by European Commission and the Joint Research Center concerning the definition of nanomaterials. Next, please. Concerning legislation that really addresses specifically nanomaterials, there is only a few. We have, of course, REACH that address now nanomaterials since 2020. Biocides, which address the nanomaterials since 2012. We have the cosmetic regulation, which address nanomaterials since longer the 2 previous one, 2009. And we have also the food regulation. So the food we can find as regulations, active and intelligent food contact material regulation. We have the plastic contact material regulation, food contact material regulation, but also novel food regulation, for example. And also the medical regulation, like medical devices, directly addresses nanomaterials. Here, I only present legislation that have a definition for nanomaterials. It can be differ between the different legislation. For example, we have cosmetic, food that have specific definition. And we have also a biocide-rich and medical devices regulation that applies the EU recommendation for the definition of nanomaterial, for example. But it also exists some legal text that addresses directly nanomaterials without any definition or doing a link with other legal text. It's a case for some regulation related to food. Next slide, please. And now I will enter a bit more into detail concerning the current status on nanomaterial in chemical legislation, so REACH and then CLP and the battery regulation. So in case of REACH, as mentioned, it explicitly addresses nanomaterials since 2020, when a new modification of REACH annexes was published in 2018. And it integrates the definition of nanomaterials. But we have to have a look more closer on this definition because, for example, REACH do not use nanomaterials term. It's replaced by nanoform. But the definition itself is the one given by the European recommendation. So what are now the requirements related to nanoform under REACH? It is mandatory to characterize each nanoform, especially concerning the registration process under REACH, which requires that manufacturer importers register substances about 1 ton per year. And once the substance is characterized, the information about the substance on nanoform need to be indicated in the registration dossier. Following this obligation, when you are doing a registration, you have to provide specific information in your dossier. This information depends of the tonnage you have to register. So more you have, bigger the tonnage is, more information you have to provide. And now the annexes related to information to include in registration dossier also include information related to nanoforms. Nanoforms need also to be taken into account in the chemical safety assessment and the downstream user chemical safety assessment. So this chemical safety assessment, it's required to be done when a company have to register about 10 tons per year of a substance. So they have to do this assessment and provide a chemical safety report and also exposure scenarios that will be included in the safety data sheet. There is the same assessment for downstream user, but it's mainly done when the downstream user cannot, is obliged to do it. Because when you have a use of a substance, as user, you can ask to your supplier to take it into account in your registration dossier. But sometimes the supplier don't want to do so, and the downstream user has to do his own chemical safety assessment. So in that case, also they have to integrate information about nanoforms. And I also added the obligation related to the safety data sheet that related to an amendment of the Annex 2 REACH published in 2020. And this amendment entered into force in 2021, but with transitional period, as it's usually done with REACH and CLP. And it's now fully implemented since last year. So it's mandatory to include information related to nanoform, more specifically in the section 1. This section, it's related to the identity of the substance. So now if there is a nanoform, company has to put just nanoform close to the name of the substance. Also, information need also to be in the section 3 related to the composition of a product. So in case there is a nanoform, it needs to be indicated. And the last part that requires to have information about nanomaterials, it's a section 9 related to physical, chemical properties of the products. Next slide, please. Concerning the CLP regulation, in that case, it does not explicitly address nanomaterials. But in general, nanomaterials are considered as chemical. So here, nanomaterial will directly fall under the substance, the definition of substance under CLP. So basically, there is no additional requirements when you have a nanoform. You just have to apply obligation related to a normal substance. That means that you need to classify this substance by using harmonized classification, which is a legally binding classification. Or if the classification does not exist, you have to do it by a company have to self-classify a substance. It's also mandatory to notify the substance to the classification and labeling inventory, so it's directly linked to obligation to classify. We can find harmonized classification and classification only notified by company. And also under CIP, if the substance is dangerous, you have obligation to communicate hazards through the labeling and the packaging. So in CLP, it's really generic, as nanomaterial is not directly defined in that legislation. Next, please. And my last slide, it's a legal requirement concerning nanomaterial in batteries, especially related to the regulation just published last year. So here also, there is no definition of nanomaterials, and there is no explicit requirements for nanomaterials. And again, we are like CLP, nanomaterials, chemicals, and it will fall under the definition of hazardous substance, which is given in this regulation. So as main requirements concerning hazardous substances, concerning the new regulation on batteries, so there is like similar to REACH, a restriction process. So all substances restricted under battery regulation should not be used in batteries. Similar to CLP, there is a need to provide information related to the hazardous substances on the label of the batteries. There is also a point specifically to the waste management, and there is an obligation to provide also information on hazard substances present in the batteries, especially regarding the prevention and the management of the waste batteries. And last point here we should mention is that obligation also to include information in the battery concerning the hazardous substances. So normally with this regulation, you should find information about nanomaterials, but it's not really specific to nanomaterials. And next slide. So as regulation and legislation, it's quite huge, and we can spend hours to present everything. So I put some useful links. If you have the presentation, you can have a look on it. And it's what I can do about the current status of nanomaterial in the two main chemical legislation and in batteries. And at that time, we have no information about new developments around nanomaterial, and it's will be in the future really explicitly taken into account in battery regulation. So thank you for your attention.
Thank you very much, Madame Lorraine. Please stay online. We are having our last presentation now from Alberto Capra. Alberto Capra is going to present nano in products, importance of the informed decision-making process. He's the director of the Basel Convention Regional Center for South America. Thank you, Alberto.
Thank you, Lilian. I have a presentation. First of all, I would like to thank the invitation to this panel. I'm honored to share this presentation with some distinguished delegates that an expert that we are here to talk about this topic, and especially in the frame of the Open and the Working Group 14 and in the development of the technical guidelines of the Basel Convention. BRC Argentina is based in Buenos Aires. It depends on the INTI, which is the Institutional National of Technology Industry in Argentina. And you can go with the next slide, please. So we will try to be brief because of the time. We are after time, I know. Why is important the topic of waste in the development of the guidelines? Is because waste containing nanomaterials is an emergency safety concern, as we see from the previous presentation. And the waste generating fall into three main categories: the manufacturing waste materials, like products of the manufacturing process consisted of engineered nanomaterials as a single fraction, end-of-life nano-enabled products, and waste unintentionally contaminated with this kind of waste containing, for example, in cosmetics. Next slide, please. So in the frame of the Basel Convention, we have a report. Nanomaterials is a topic that is we have quite a lot of years we are discussing about. And this report has very useful information, especially in reference of effects of engineered nanomaterials on human health and environment. And as well, talk quite a lot about what is the potential risk in the occupational hazard, modeling exercises, municipal solid waste, incineration, landfill, information. Sometimes it says the report that information about nanomaterials in products and waste sometimes is poorly described, and we don't have quite a lot of information in the environmental sound management of products and wastes. And there is quite a lack of information about the best technologies and best practices in relationship of the waste. And a very big problem in the classification of the waste, if it is the hazardous or not. And this is related to the infrastructure they need and the flows as well. Next slide, please. That's why it's important the information decision-making process. Why? Because in the frame of the risk assessment and management, IDMP allows for thorough risk assessment to identify potential toxicological effects, exposures, pathways, and the population risk. Of course, because of the regularity compliance, IDMP ensures compliance with environmental regulation and standards, reducing legal liabilities and fostering best practices. Next slide. Also, IDPM has to do with sustainability, because the effective of waste management practices derived from IDPM can enhance resource efficiency, promoting the recycling and reuse of nanomaterials, and prevent or minimizing wastes. And lastly, because of transparency, providing clear and accurate information about the risks and benefits of nanomaterials in key to build public trusts. Next slide, please. So, what about in the framework of the chemical waste agenda programs and negotiations? IDPM, it was included in a way in the resolutions of UNEP, UNEA 1/5 on chemical waste, because there it says it's necessary to improve access and generation of information, as well as in the framework of the global framework of chemical, this new framework approved last year. And there we have the improving of transparency and access of information on chemical and its associated risks. And just a few days ago, the second meeting of the executive board of this relevant new framework gathered in June here in Geneva, and in the draft guidelines for the project request cycle on the facility, so that the country has to apply to this new fund. There was a topic about the integration of some management of chemical and waste into sustainable development decision-making processes as appropriate. So this topic is included as well. Next slide, please. So, as I said, the global framework of chemicals, they have a strategic objective on comprehensive and sufficient knowledge data of information. The next slide, with goals and targets. So, why is important and the relevant issues? Given the anticipated increase in the production of engineered nanomaterials and potential environmental emissions, policy should be based on the precautionary principle to regulate their waste. There should be an informed and participatory decision-making process that includes all relevant stakeholders. The report of the Basel Convention from 2018 as well highlighted the need of the apply of the precautionary principle in these regards. There is a rapid and diverse growth of engineered nanomaterials. It is difficult for regulators and risk assessors to understand the potential for the exposure to these nanomaterials and whether methods used for assessing risk of conventional chemicals can be used for nanomaterials. It's totally different for the management of the use as battery itself compared with a waste containing nanomaterials, for example. The infrastructure and the management is totally different because if there is no information about that, we don't know how to apply as regards risk regarding the environment, the human health, and the workers. So it is important to have studies in Latin American region about this risk in order to make informed and science-based decisions in this regard. So as I said before, technical guidelines that provide information on best practices and techniques would be needed, especially within the framework of the Basel Convention, and the report of the 2018 is a good example, and this could be broadly discussed in the development of the technical guidelines of use lead-acid batteries and the others as well. To have the necessary information to develop regulation and adequate management procedure, especially for the developing countries. Next slide, I think that this is the last. So thank you very much.
Thank you, Alberto. Thanks for bringing the low and middle income countries and regions to the floor. And now I give the floor to Judith Torres from the Ministry of Environment of the Government of Uruguay to continue with the coordination and the final part of the side event.
Thank you very much, Lilian. Thank you very much for all the participants that we have in this table today. Really, we have distinguished participants with high information, and here first of all I need to thank Francesca Ceni and Mermush Asodi for their kind help in the organization of this side event, in the networking and connecting us with the specialists that we have the privilege to have this evening. Certainly we have difficulties in the information access to these nanomaterials in different products. One issue that is lacking is labeling. So I think that yes, we have an important issue in this regard. So at that point in the evening, I invite you to make some comments or questions to our distinguished speakers. Please go ahead.
Thank you very much. My name is George Karlaganis from UNITAR. First of all, I would like to thank GAHP and the Government of Uruguay to organize this important side event tonight. Actually, I would like to remind you that of the topic waste containing nanomaterials is on the agenda of this meeting in item 3, D, Roman 5. And there is a document 14/8 and also an INF document, and I read quickly out the proposed action in this document. It's written in paragraph 3.4.2. The open-ended working group may wish to adopt a decision along the following lines: invites parties and observers to make available to the Secretariat by the end of December 2024 any new information related to activities amended at addressing issues related to waste containing nanomaterials, including case studies about and best practices relating to the management of waste containing nanomaterials. So I do hope that many parties to the Basel Convention will support this proposed action. This would then allow all stakeholders to send in information by the end of the year, and I do hope that also the presenters of this event of today will then hopefully send out their information to the Secretariat by the end of the year. Thank you very much.
Thank you very much, Unitar, for your comment. We have seen this topic of nanomaterials for several years since the SciComm emerging issues, now in the Basel Convention, and we know that this topic has not been prioritized in other programs of work. Let's see what happens in this one. So I don't see other requests for the floor. We have some questions for our speakers, and I would first address Dr. Vivian Howard, and ask what is the main hazard to avoid with nanomaterials during battery disposal? You have the floor.
Okay, thank you very much. I want to apologize. I don't seem to be able to get my camera working, but at my age, maybe that's not such a bad thing. Right, well, as I think I said in my talk, a major portal of entry is by inhalation. And then the nanomaterials could gain access directly to the bloodstream via inhalation. So that's definitely one to avoid. And there's the 6-city study from America, and there was a similar European study, and they all show that inhalation of small particles is injurious to health. So that would be that, but water as well. I mean, there are papers out now showing damage to ecosystems through nanoparticles being distributed in water. So I think we just have to be rather precautionary in our approach and try and make sure these materials are disposed of in a closed system.
Thank you very much for your answer. Now I will direct another question to our distinguished Claude Chanson. How is the risk of nanoparticle emissions controlled in the battery industry?
Yeah, thank you for the good question. Indeed, as you know, the big benefit of electrification, which is strongly promoted today, is to remove particles of carbon dioxide or emissions particles for the internal combustion engine by batteries. And the purpose, of course, is not that batteries generate again microparticles. That's indeed a very good question. So we have been related to managing particles in batteries for a long time. You just saw that we are now coming to nano particles, but the questions of protecting workers has been set for a long time. And indeed, now the fact is that battery manufacturing is becoming a kind of, like electronics manufacturing, semiconductors and so on. Dry rooms, very clean rooms, no exposure at all, because you are really in a very clean environment. But that's for the manufacturing. Then the question is also more important for the recycling and the waste and the end of life. So we are also promoting, of course, that recycling plants are having the level of protection required by the workers, and that's applicable mainly in Europe. You saw a number of regulations. One of them was even not mentioned. It's an industrial emissions directive, which is applicable in Europe, which is measuring the exposure level in the particularly battery recycling plants are submitted to this industrial emissions directive. And then you have these so-called OELs, so overall exposure level for the workers and so on, which are agreed and of course need to be updated according to the level of the particles we are discussing. The more fine they are, the more strict has to be the regulation, but that's something which are following. And that's what I can say about the European battery industry, which is indeed prepared and under control as far as possible. No industry is perfect, but at least there is regulation. But really, we focus and support the Basel Convention activity to make sure that these equivalent conditions are applicable all over the world and not only in Europe, because battery is enforced a world business with world trade and world exchanges. So a battery produced in Europe and made in your phone or your laptop may perfectly end up in any country in the world before it is recycled.
We have some question online.
Okay.
Yes, we have some questions from the box online. The first one comes from Roshan Abbasov, and it is there an increased trend of nanomaterials due to the increase of electric mobiles?
Well, I would say electrification when it's related to batteries, of course, imply that you are using up-to-date design of batteries. And as I mentioned in my talk, indeed, there are studies demonstrating that fine particles and then nanomaterials particles could behave better and have more efficiency and better material usage. So I believe here the objective is indeed to make this best product available just for competition and for the service of users, and make the electrification become, in fact, an act which is moving toward global health and safety, and then not moving toward more risk attached to the battery. So indeed, more nanomaterials may be used in the future in batteries. That's a trend that I mentioned. And attached to it, we need to maintain a high level of control of the risk, particularly at end of life.
Thank you very much. Lilian?
Yes, sorry for taking the floor, but I have a question for you as well. On the conditions of work, due to the lack of information of the nanomaterials being included in lead-acid batteries and not lead-acid batteries, do you think that can be a very important difference in the conditions of work in the workers out of Europe and in Europe, because in the fact the access to information is central, no, to protect workers?
Well, I think we should differentiate about what is the best available techniques, which can be discussed, and indeed there are always work ongoing. And you have seen, I was talking about batteries technology, which is evolving. And then attached to that, you need to have also best available techniques evolving. But the issue you are mentioning, it's more about not identifying the best techniques, but implementing them. And unfortunately, a lot of these decisions are cost-driven. And depending on the various country regulations and let's say, level of competition, I recognize that different level of implementation are at the present time in the worldwide, including, for example, lead-acid battery recycling. We recognize that there are places where the conditions of recycling are not, let's say, coherent or comparable to what's happening in Europe.
Thank you very much. There is another question online. Please, you have the floor.
Lucille, can you share the question with us?
Lian de Bouquer has asked, are nanomaterials present in black mass? Does the EU battery regulation specifically require disclosure of nanomaterials in the battery passport?
I'm not sure I get all the question. My understanding is that, first of all, yes, the black mass is, for people which are not aware, is a result of crushing batteries. So you generate powder. And indeed, this product is considered in the European regulation now as an intermediate recycling fraction. So it's started recycling because you crush the battery, but the black mass by itself is just a mixture of all the elements you add in the cell. So it's not finished recycling, it's not final products. Nevertheless, this black mass is traded, that's a fact. What we promote at the moment is that this trading is happening under the conditions of hazardous waste. And there is a European regulation for waste trade, which has been updated this year, which clarify the conditions for shipping hazardous waste, and including black mass, which respect, in fact, the Basel Convention, which means that you are not expected or not allowed to export such type of product to non-OECD countries, first of all, and these kind of criteria. Then I think that was a part of the question I took. I may not get all the questions, I'm not sure.
Thank you.
Maybe I would say for second part is more related to battery regulation, so maybe I can answer on that. Just, concerning specific disclosure on nanomaterial in battery passport, as mentioned, battery regulation for the moment do not explicitly address nanomaterials, but you have to provide information on the dangerous substances. You have a specific annex mentioning what you have to put in a battery passport. And concerning materials of the battery, you have to include, of course, what substance, hazardous substance you have in a battery, but also the different chemical characteristics of the different components of the battery. So I guess you will have, if you have information about nanomaterial, it will be to be included in that way in the passport. But there is no at that time specific obligation and disclosure about information on nano.
Thank you very much, Lorraine. I have a question for you regarding the legislation. And the question is, does the legislation that explicitly addresses nanomaterials use the same definition? If not, why does this definition differ?
Concerning nanomaterial definition, no, unfortunately, it's they are not all using the same definition. I would say in general in legislation, it's a critical point to not have the same definition of a similar term. But one explanation is that, for example, in food of cosmetics, they have their own definition of nanomaterial, and it was in place before European Commission published the first recommendation for definition. And if I take, for example, the food legislation, we have not, it's similar to REACH, they do not use nanomaterials term, they use the term engineered nanomaterials. But in the definition is quite similar, but not. And then you have other legislation that directly implement the Commission recommendation. But in the future, we hope that we will have an alignment of the definition with the new revision of the different legal text to be sure that we have something aligned and not too much different. Because I would say definition, we know that in our work as a help desk, that definition are always important. But you have also the difference, second reason about this difference, it's also because legislation have their own have different boundaries concerning what they are addressed or not in their legislation. In case of REACH, for example, they do not address incidental substances, for example. So this is the two main reasons that explain the difference between the definition and the different legal text.
Thank you very much, Lorraine. I have the last question, and it is for Alberto Capra. Based on your experience in managing chemicals at regional center in recent years, what information do you consider essential for the informed decision-making process in this ESM of waste? Thank you.
Thank you, Judith. I think that the existence and concentration of nanomaterials in products are very relevant, because then you can study and decide if this waste is hazardous or not, and is it hazardous one way and if it's not hazardous is another one. So especially because of the risk to the environment, to the workers, and to the health. So we need to know the type of quantities and the waste generations, because we need as well the ability of infrastructure and the capacity to manage these wastes. So that is why very relevant in the products to have this type of information.
Thank you very much, Alberto. Is there any other comment or question from the floor or the online participants?
Yes, we have one question from, just give me 1 second because I lost him. Abraham Matiza, he had been waiting for a while. If you still have your question, Abraham.
Yeah, can you hear me?
Yes.
Yeah, no. My question is, in terms of nanomaterials developing countries, also that the battery industry is, particularly the EVs, are on top. I mean, you know, we don't have that capacity now to kind of determine now what's coming in or what's going out. Are there any measures in place also to assist developing countries or countries in transition in terms of this issue? Thank you very much. Over.
Thank you very much, Abraham. We have been dealing with these nanomaterials issues since 10 years, trying to make information available. Also, as we have learned from our speakers, industry is evolving and nanomaterials is being included in different types and in different ways in different products. So this topic on our table is the first step to help developing countries that are dealing with the importation of these articles and products that we do not produce in our countries. But we are not. It was an interesting side event. There were very important information and insights on this issue. We are almost 10 to 8, so I would like to close this event, thanking Secretariat, thanking UNEP, thanking all the speakers that were willing to deliver their information in this important side event. We are grateful for all your time and knowledge to this issue. Lilian?
No, thank you everybody to be here, for being here. In particular, this has been very useful to clarify and to help to our work from now on. And I expect that the visibility of the nanoparticles and nanometals will be increased in the importance of the focus of the Basel Convention. Thank you very much, and good afternoon for everybody.